Okay, we're going to get started today, so please settle in. All right. Can you guys hear me? Does that work? Okay, yeah, we're gonna start right away. So I have in here a flyer for AMSA, one of the many pre-medical organizations we have. They have a meeting, so look at that information in the notes when I post them in Blackboard if you're interested. And if you want me to promote your event or organization anytime, just let me know. As long as you're not trying to shake down your fellow students for money, I'd be happy to do that. So we'll get right into today's class, because as you remember last time we had to end a little bit early because of some technical difficulties. The first time in my career I had to end class early because of that, so hopefully that's the last time, or else you guys will start to think that I'm a boomer who can't use technology or something like that. But anyway, we're going to continue on where we left off last time. So we started talking about the three mass laws, and we got through the first of them before the tablet flaked out. So the first one we talked about was the law of conservation of mass, which states that mass is conserved during a chemical reaction, matter is neither created nor destroyed. And then, so we are continuing at the end of last class's notes. If you're trying to orient yourself, we're going to pick up those last few slides, then move on to the new stuff as soon as possible. So the second one is the law of definite composition, and this one is credited to Joseph Proust. I'm not sure if I'm saying his last name correctly. It might be Proust if he's German, but nonetheless, this is the scientist you should be familiar with as coming up with this law. And what this deals with is the composition of a compound in terms of the elements that make it up. So remember, a compound is a substance made up of two or more different elements, and every compound has a specified composition of those elements. So the way to state this would be that a given compound always contains the same proportion of elements by mass, regardless of the source of that compound. All right, so if you get water from the fountain out in front of this building, or if you get water from a puddle in your backyard, or you find water on the surface of Mars, they are always going to have the same proportion of elements in that water. In that case, it would be hydrogen and oxygen, as you probably know. Okay? So we're talking about mass ratios here, and a given compound always contains the same proportion of elements by mass. Again, the key aspect of this is regardless of the source. So it doesn't matter how you make the compound, where you get the compound from, it's always going to have that specified mass ratio for that compound. So then, as an example of this, let's talk about a very common substance that you've heard a lot about, which is carbon dioxide. So if we have 44 grams of carbon dioxide, which these numbers will make, why I'm choosing these numbers will make more sense a little bit later on. But anyway, if we have 44 grams of carbon dioxide, it's made up of carbon and oxygen, and it's going to contain exactly 12 grams of carbon and exactly 32 grams of oxygen. All right, and again, the sum of the two masses of the elements has to equal the mass of the compound, so 12 plus 32 is 44, and that's always going to be, if you have any sample of carbon dioxide with a mass of 44 grams, it will always have 12 grams of carbon and 32 grams of oxygen. Now, what this allows us to do then is to define a parameter called mass percent. So we don't want to always talk about things in absolute terms, but if we want to talk about things in a more relative sense and be able to do sort of an apples-to-apples comparison between different compounds, it's more convenient and more useful to define a mass percent. So for every element in the compound, you can define this parameter called mass percent. So in carbon dioxide, the mass percent for oxygen is the mass of oxygen in the compound, which is 32 grams, divided by the mass of the compound, which is 44 grams, and then you multiply that by 100 to convert to a percent. So anytime we say percent, that's out of 100, so you have to multiply by 100. If we said mass ratio, it would just be the two numbers divided by each other between 0 and 1. And so what you get for oxygen is 73%. And you can do the same thing for any other element in the compound. In this case, for carbon dioxide, the only other element is carbon. So if you do the mass percent for carbon, there's 12 grams of carbon, 44 grams of carbon dioxide, multiply by 100 to get a percent, and that comes out to 27%. And as you should recognize then, these two numbers added together should be 100%, which they are. Okay, so the sum of the mass percents for every element in that compound will equal 100. If it's only 2 elements, it's only 2 percentages that add to 100. If there's more than 2 elements, then however many percentages you have will add up to be 100. So in general, the mass percent of an element in a compound is the mass of the element divided by the mass of the compound times 100. Okay, and that's a new parameter then that we can define that's related to this law of definite composition, dealing with the composition of elements in a compound. So let's do a couple of sample problems related to this. This is really the first type of numerical problem we face. The beginning of the course is not terribly quantitative, but this is one of those things where we'll have to do a little bit of computation. So let's say we have the compound pyrite, which you may know of as fool's gold. It's not gold. It kind of looks like it, but it's not. It actually consists of very cheap things, so it's not valuable at all. And it consists of iron and sulfur. Those are the 2 elements in pyrite. And if you have 50 grams of pyrite, that would contain 26.7 grams of sulfur. And what this question asks is, what is the mass percent of iron in pyrite? Now, whenever you're starting a problem that's a word problem like this, which is most of the things we'll give you in this course, the helpful problem-solving strategy I like to follow is go to the end of the problem first and figure out what it's asking you. Because if you know what it's asking for you, then you can figure out what information do I need to get that response. So we are looking for the mass percent of iron, and as we just defined, mass percent of iron would be given as follows. It's going to be the mass of iron in the compound divided by the mass of the compound itself, which in this case is pyrite, and we're going to multiply that by 100. Okay? And so we just need 2 numbers then to get the mass percent, the mass of iron and the mass of pyrite. And very often, one or more of these numbers will be given to you directly in the problem. So we see that we're dealing with a 50-gram sample of pyrite, so that we already have. So we have the denominator here already is 50 grams. That's how much pyrite we're talking about in this problem. But now we figure out the mass of iron, and that is not given directly to us. Okay? So the mass of pyrite is given to us directly. So let me write that out again. That's given information. So very often, one or more of the numbers you need is given. But we need the mass of iron, and we're not given that. We're given instead the mass of sulfur, which in this problem is not particularly useful to us. But we have to recognize that, again, the sum of the masses of the elements has to equal the mass of the compound. So the mass of iron plus the mass of sulfur has to equal the mass of pyrite, which is 50 grams. All right, and so these little 3 dots mean therefore, and that means we just do a subtraction to find the mass of iron. So we have 50 grams of pyrite. We have 26.7 grams of sulfur, and the rest has to be iron, which is 23.3. All right, so that's the number we're going to use then in the numerator up here to find the mass percent of iron. And what that comes out to then is 46.6%. Okay, so this was an example of calculating a mass percent. Just be aware that sometimes we don't directly give you the masses, but the sum of all the masses, again, has to equal the mass of the compound. Or alternatively, you could find the mass percent for sulfur, which is given, and then subtract it from 100. There's a couple ways to get that same number. You'll get the same result either way. Okay, so that's how we deal with calculating mass percents. And then the other thing we need to be able to do is use mass percents. Okay, so we're going to use them now sometimes as conversion factors in other types of problems. So here we gave you the same given information. 50 grams of pyrite contains 26.7 grams of sulfur, but now we want to know how many grams of sulfur are in a 1.235 gram sample of pyrite. So we know this is how much sulfur is in 50 grams. Now we want to figure out how much sulfur is there in 1.235 grams. And we're going to do this, again, using the mass ratio or the mass percent as a conversion factor. Now we already calculated the mass percent, so we could use that in this problem. But even if we hadn't done that, we still have the information we need because we have, again, the mass of the compound and the mass of one of the elements that's in that compound. So what we're looking for in this problem, again, go to the end of the problem to look what it's asking for. We're looking for how many grams of sulfur are in this sample of compound. All right, so when you're solving problems, again, you try to start with what you're looking for, and then you have to identify a starting point. What do we know? Well, we know that we're starting with 1.235 grams of pyrite. We want to figure out how much sulfur is in there. So now we're going to use what's called the factor label method to convert grams of pyrite into grams of sulfur. And in this case, we can do that in one step. Okay, so we're going to make a ratio that involves two masses that are given to us. So we want grams of pyrite to cancel, so that has to go in the denominator. My high school physics teacher hated the word cancel. There's no mathematical operation called cancel, but we want it to divide out if you want to be precise. So we need to put grams of pyrite in the denominator. We're given, again, that we have a 50.0 gram sample of pyrite where we know the mass ratios. And then we're trying to convert to grams of sulfur, so that's going to go in the numerator. And we know that our 50 grams of pyrite contains 26.7 grams of sulfur. In this case, we'll use that number directly. Okay, so grams of pyrite divides out. That gives us grams of sulfur, which is what we're looking for, and we can stop. So you really need to get in the habit of writing out your units when you're doing numerical problems like this, because it really orients you on which numbers you need to multiply, which numbers you need to divide, what order you need to do things in. If you're just writing out a string of numbers, you're bound to make mistakes. So I'm going to emphasize that over and over again in this course. I'll sound like a broken record, but you'll get used to it. Okay, so that tells us then we have 0.695 grams of sulfur in our 1.235 gram sample of pyrite. All right, and what this problem shows us then, which is another important aspect of the law of definite compositions, is that mass ratios, or mass percents as they can also be stated as, they can be used as conversion factors. All right, and that can work in a lot of different ways. So here's one example of it that I gave you here, but keep in mind that what we can do is if we have, you know, two elements in the compound A and B, we can figure out how much of the other element would be present in the same compound. Or we can convert either of these using the mass of the compound itself. All right, so when you're setting up problems like this, be aware that you can use a lot of different possible ratios. It can be a ratio of two elemental masses to convert the mass of one element into another, or it can be the ratio of one of the elements to the mass of the compound if you're trying to figure out, like we did here, how much of that element is in the compound. So there's a few ways it can work. So again, the best way to practice this is by doing the homework assignments, where you'll get some problems that are along these lines. All right, so any questions on definite composition or mass percent? Okay, so if now we're going to move on to the third and final of the mass laws, which is the most convoluted, I would say, the most complicated. Now, what I would say about this mass law, multiple proportions, is if you're answering questions on the homework assignment or the test that deal with the law of multiple proportions, the dead giveaway is that you are dealing with two or more different compounds. Okay, so the first mass law was mass conservation. That one was pretty easy. The law of definite composition that we just covered deals with the composition of a single compound. For multiple proportions, we're talking about the composition of two or more compounds and how those compositions are related to each other. And the specific situation we're dealing with the law of multiple proportions is when you have two different compounds that are formed from the same elements. So an example that you're probably familiar with would be, for example, carbon monoxide, carbon dioxide. Both carbon and oxygen, but different ratios of the two elements, so they're different compounds. Or water and hydrogen peroxide, both hydrogen and oxygen, but different ratios of those two to make two different compounds. So that's the situation we're dealing with law of multiple proportions. Now, there's not really a simple and concise way of stating this law, but basically what it says is that if you have 1 gram of element A, so I'm just using generic letter abbreviations for elements, but this can be anything, and it combines with element X, a different element, to form two different compounds. It could be more than two, but typically we'll just do it in the context of two compounds. So first of all, what has to happen is that the ratio of A and X, the two elements, has to be different in the two compounds. That's what distinguishes them from each other. That's not 100% true, but for our purposes, that's fine to think about it that way. And then what has to happen then is that the masses of X that combine with A, so for the first compound, 1 gram of A is going to combine with some amount of X to form the compound. For the second compound, 1 gram of A is going to combine with a different amount of X to form the different compound. And the ratio of those masses of X that combine with A are related by simple whole numbers or small fractions. They're small whole number ratios of each other. So those two masses of X that combine with 1 gram of A to make the two different compounds, their ratio is going to be something like 2 to 1, 3 to 1, maybe something like 3 to 2, and so on. But it's not going to just be any random ratio. It's not going to be like 2.767 or something like that. It's not going to be 1.085. It's going to be a relatively simple either whole number, 2 to 1, 3 to 1, or maybe a simple fraction like 3 over 2 or maybe 3 over 4, something like that. So they're always going to be related in those pretty simple ways. So you're talking about, again, the ratios of two different compositions in two different compounds. So let's just illustrate this numerically, because writing it out, as I said, is kind of wordy and confusing. So let's just do it for a real example. So here we have two compounds that are made from iron and oxygen. One of them you're familiar with, which is rust, which if you lived in a cold climate, you would see it all the time, especially. And then another one is called ferrous oxide. And again, they're both iron and oxygen, but different ratios, as you can see. So the mass percents of the two elements are different in the two compounds, because that's what has to be true for them to be two different compounds, even though the elements themselves are the same. So what we're going to do to sort of demonstrate the law of multiple proportions is we're going to calculate a mass ratio. Now you can calculate whatever ratio you want and just compare them as long as you're doing the same one for each compound. So what I'm going to do is for ferrous oxide, I'm going to calculate the mass ratio of oxygen to iron. And that's going to tell us how much oxygen reacts with 1 gram of iron in this compound. So that'd be a way of normalizing it to the mass of iron. And we can do that using the mass percents that are given, because remember, mass percents are how many grams out of 100 grams you have of that element in the compound. Okay, so we're going to have 22.27 is the mass percent of oxygen. That's 22.7 grams of oxygen per 100 grams of compound, and 77.73 for iron. That ratio is 0.2865. And that can be interpreted as, if you have 1 gram of iron, you would react it with 0.2865 grams of oxygen to make this compound here, ferrous oxide. Now, what the law of multiple proportions tells us is that the same ratio for rust, the other compound with iron and oxygen, should be a relatively simple multiple of this number. It's not going to be this number times, again, any random number. It's going to be this number maybe times 2 or times 3 over 2 or times 3. Some simple multiple of this number would represent then the same ratio for rust. So let's see if that's true. So if we calculate the same thing for rust, same exact ratio, mass of oxygen over mass of iron, but different numbers now because it's a different compound. What we end up with is 30.06 divided by 69.94, which is 0.4329. So that means for this compound, if you had 1 gram of iron, you would need to react it with 0.4329 grams of oxygen to make rust. Okay? And now if we take the ratio of these two ratios, the ratio of ratios, which sounds confusing, but that's what we're doing, we should get a small whole number or a simple fraction, and we do in fact get that. So these two divided by each other is 1.500, which we'll recognize can be written as a simple fraction 3 over 2. All right, so this is just a demonstration of that using real numbers. That's all this was, okay? So again, two different ratios for two different compounds, and the relationship between those is a simple whole number or a small fraction, not a complicated decimal number or anything like that. All right, so that's what law of multiple proportions tells us. We're not going to do too many numerical problems with that. The important thing is to know the concept. And again, the key dead giveaway of this concept is that we're always comparing two different compounds that have the same elements in them. So that's when the law of multiple proportions applies, and there are many situations in the real world where that does happen. As we talked about a couple here, carbon dioxide, carbon monoxide, water, hydrogen peroxide, or this example with iron and oxygen. All right, so that's the last of the mass laws. We're not going to do any more in detail with that one. But let's review the three now, because what these are going to lead to then is a unifying theory. So as we talked about the scientific method at the beginning of last time, a law tells you what happens. So those three mass laws tell you very distinct observations about elements and compounds and how they react with each other and how they combine with each other. And then we're going to use these three mass laws to generate a theory, or we're not going to, the previous scientists did many years ago, to generate a theory that explains all of them. Why are we seeing these three observations that are all related to each other? So let's review the three first, just to make sure we have them all together. So as we talked about last time, conservation of mass is that mass is neither created nor destroyed during a chemical reaction. All right, so that's law of conservation of mass. That one I think is pretty intuitive. The one we just started with today is definite composition, which is that each chemical substance, in particular we're talking about chemical compounds here that have two or more elements in them, but every chemical substance has a specific proportion of elements by mass. Now, if your substance is an element, like pure carbon, for example, the mass percent will just be 100% carbon. There's no real, I mean, it's a trivial outcome. But in any compound that has two or more elements, they're going to be defined by a specific mass ratio of the elements in that compound. And then the one we just talked about is the most wordy and confusing, but it deals with a situation where two elements combine to form two different compounds, two or more different compounds, I guess, in particular. All right, so two of the same element, the same two elements combine to form multiple compounds. Very common situation. And each compound has a distinct mass ratio. That's what distinguishes the two compounds from each other. And then furthermore, if we take the ratio of these two ratios, all right, so we find the mass ratio for one compound, the mass ratio for the other, and we divide the two by each other, that ratio of ratios will be a small whole number or a simple fraction. All right, so that's the law of multiple proportions. So these three together have been known for a long time as the three mass laws. And then what happened after that was a scientist named John Dalton came up with an atomic theory to explain these. Okay, so again, these were all observations. This is what happens, but why is it happening? And he came up with the atomic theory to explain all this. And it's helpful for you to think about the relationship between the laws and the theories. How do the observations that we just presented lead to this theory, this explanation for them? So the atomic theory has a few different points that are made, and it can be divided up in different ways. I'll sort of do it with four main points here. You might see it categorized in other ways in your textbook, but nonetheless, I'll give it to you in this way. So the first is that substances are composed of tiny particles called atoms. Let me spell the word tiny correctly. And the key aspect of atoms, I mean, the name is atomic theory, so of course it deals with atoms, but these atoms cannot be decomposed further. So basically it's the smallest piece of matter that you can have. You can't break it down any further. Okay? And another key point of the atomic theory, and this relates to conservation of mass in particular, is that the atoms cannot be converted into different atoms. And this one kind of blows the alchemists out of the water, right? Because they were spending centuries trying to convert lead into gold, and they thought they could do it, and turns out they were wrong. Because according to the atomic theory, which is largely true, I'm not going to talk about cases where if you're on the surface of the sun, you can convert one atom into another. But under regular conditions on Earth, you can't convert atoms into different atoms, which also again then means that elements cannot be interconverted. So if you have carbon as part of your reaction, it's going to remain as carbon the entire time. It's not going to change into a different element. All right, so you can't change one element into another. That's basically what that says. And then the other two sort of deal with how are atoms different from each other that make up the different elements, and also how do they combine then to make compounds. Okay, so if you have, so atoms of a given element, so what makes one element different from another is a function of the properties of their atoms. So atoms of a given element have the same mass and other properties, and they're distinct from other elements. So basically, every different element is made up of atoms that are different from each other. Not too surprising if we're talking about the composition of matter being made up of these atoms, okay? So that means the atoms that make up carbon have a different mass than the atoms that make up oxygen, which have a different mass than the atoms that make up iron. Now, this, as we'll point out a little bit later today, I'm going to put a little star next to this because this one is not entirely correct. So as we said, science develops over time. Sometimes theories get refined and things about them may not be 100% true. It's not, as we'll see, true that all of the atoms for an element all have the exact same mass. So there are different masses within each element that we can have. We'll talk about that later today. So that one's a little bit wrong, but more or less the point still stands that every element is made up of atoms, and the atoms of the different elements are distinct from each other in important ways. We'll talk about those ways later today. And then the fourth one, which relates to definite composition in multiple proportions, is that chemical compounds are formed when atoms of different elements combine in a specific ratio. All right, and this one's important both for, really for all the mass laws in some sense, but especially for the last two. And any chemical reaction that you would study involves reorganizations of atoms. So you're gonna, and we'll talk about all the details of this throughout this course later on, but you're gonna, change the way the atoms are connected to each other, change their ratios, that they are combined with one another. But you're not, again, creating or destroying atoms, you're just reorganizing them. Now this one is especially important for the law of multiple proportions because, remember, atoms cannot be broken down any further. And so what this means is if one compound, for example, carbon monoxide, as we'll learn later, involves one atom of carbon combining with one atom of oxygen. If you're going to make another compound with carbon and oxygen, that one atom of carbon can combine with maybe 2 atoms of oxygen or 3 atoms of oxygen, but it can't combine with 1.3 atoms of oxygen or 1.7 because you can't break down the oxygen atom any further. So that then leads to the law of multiple proportions because those ratios of masses then have to be distinct intervals of each other. They can't just be any random relationship between them because every atoms must combine a whole number of ratios because you can't have a fraction of an atom combining with another one. So think about these a little bit more. It's helpful to try to internalize them, but this is the theory that explains all the mass laws that we just covered. All right, now the next thing we're going to cover briefly is a little bit out of the scope of what we're doing now, so we're not going to talk about a lot of details, are some additional early discoveries that dealt with determining chemical formulas. So we now know that we can characterize any compound as a ratio of elements. But then how do we go further and say, well, okay, if that's the mass ratio of the elements, how do we know how many atoms of each element are in the compound? So how do we know that carbon dioxide is 1 carbon atom and 2 oxygen atoms, for example? So there were some early experiments that were done that got at those issues of actually determining the formulas of chemical compounds in terms of how many atoms of each element are present. But again, we're not going to go over a lot of the details of this just now. But there's 2 that we're going to cover just right now, just to get them out of the way. So the first is a French scientist named Guy Lussac who made an observation. He was studying gas phase reactions. So a lot of the early chemical reactions involve solids because for solids you just have to measure their masses, and so that's where a lot of the mass ratios and concepts about that were developed. But by studying gas phase reactions, we can learn some additional things. And gas phase reactions are also convenient because, as we'll learn later in the course also, you can measure a lot of things about gas phase reactions just by measuring the volume of the gas. Do the reaction in a balloon and figure out how big the balloon gets and stuff during the reaction. And volume is pretty easy to measure, just like mass is. So you can learn a lot of things by doing gas phase reactions as well. Again, think about low-tech society that they lived in when they were doing these types of experiments. So at equal temperature and pressure, what Guy-Lussac found is that gases combine in chemical reactions in fixed whole number ratios. All right, so what he found, for example, is let's say we're going to burn hydrogen. So this is an experiment that some chemistry professors do in class. I'm not going to do that because, well, the College of Education probably would not be happy if I was setting hydrogen on fire in here. And I would not trust myself to not burn something. But anyway, what would happen is if you're studying let's say the burning of hydrogen, which involves hydrogen gas, oxygen gas, two gases reacting with each other. So what he found was that in any case that he studied this carefully, you would have 2 volumes of hydrogen, so let's, for example, 2 liters of hydrogen, if you're working on that scale, would always combine with 1 volume of oxygen. And those, when they burn, they form water vapor, which at the high temperature of the combustion reaction remains as a gas. And so that always forms 2 volumes of water vapor. So it's always these simple whole number ratios for these gas phase reactions. All right, again, it's not 2 volumes of hydrogen plus 1.37 volumes of oxygen. It's always simple ratios when you're reacting in the gas phase. And this was then explained by a scientist named Avogadro, who has a number named after him that we'll talk about later in the course. But actually his most important scientific contribution was this one. He didn't actually come up with Avogadro's number. Somebody just named it after him. So Avogadro's interpretation of Guy-Lussac's observations was that if you're at the same temperature and pressure, as you were in the experiments that Guy-Lussac was doing, and we're going to come back to this later in the course, so we're not going to bog ourselves down in the details now. But equal volumes of different gases all have the same numbers of same numbers of atoms. Now I'm going to call them particles here because a lot of gases are made up of molecules, not atoms. When I say particles, I mean either atoms if we're talking about a gas that's made out of atoms, or molecules if we're talking about a gas that's made out of molecules. But they have equal numbers of particles. So if you have 2 liters of hydrogen, it's going to have some number of hydrogen molecules in there. Hydrogen exists as H2. If you have 2 liters of oxygen at the same temperature and pressure, you will have the exact same numbers of oxygen molecules in the sample. So it doesn't matter what gas you're talking about, at the same temperature and pressure, if the volume is the same, the number of atoms or molecules is the same. And so then what you can do is you can interpret Guy-Lussac's observations at the atomic level. And what you can say then is that if in this reaction of hydrogen and oxygen, 2 atoms of hydrogen, as we'll see in the next slide, this is actually molecules, but it works the same way, will always react with 1 atom of oxygen. So basically the volume ratios that Guy-Lussac observed are equivalent to the atom ratios, the ratio of the atoms that react with each other at the atomic level. So in this burning of hydrogen, 2 atoms of hydrogen would react with 1 atom of oxygen, and you would form then 2 molecules of water, exactly equal to the volume ratios that were observed before. 2 to 1, forming two volumes of the product. All right, so that's kind of how one of the early experiments that determined chemical formulas. And so with both of these being true, now if you study any gas phase reaction, if you know the ratios of the gases that are combining, you can use that to piece together the chemical formula of whatever product is forming. In this case, water being 2 hydrogens to 1 oxygen, as we all know, H2O. Okay, here's sort of a little picture of how this works. So it turns out that most gaseous elements are diatomic, so hydrogen is not just hydrogen atoms, but it's H2, oxygen is O2, and so on. So that's a little point that we'll get to later. But if we're studying these reactions, the one that we just talked about was if you have 2 hydrogen molecules, which are, again, each of them is 2 atoms of hydrogen bonded together. So at a macroscopic level, it's 2 volumes of hydrogen. which at a microscopic level would correspond and would be related to two molecules of hydrogen. And if you combine that with one volume of oxygen, which would have then, in relative sense, one molecule, and then what you form is two volumes of water at a macroscopic level. And in order for that to be true, the ratio of hydrogen to oxygen in the final product water has to be 2 to 1, because you're combining 2 to 1 and you're making two molecules of water. So the only way for that to work is if water has this basic formula here. Oxygen bonded to two hydrogens each. All right, so that was how they would have figured out then the formula of something like water. This is the only way that can work. If you combine hydrogen and oxygen in any other ratio in the product, you wouldn't be able to make two molecules of it. And so in order to make two molecules of water, they have to have a ratio of 2 to 1 hydrogen to oxygen. So that gives you that chemical formula of H2O. Now, a slightly different one is, let's say we react hydrogen with chlorine gas. And what they found is if they react hydrogen with chlorine, they react in a 1 to 1 ratio. So in this case, one volume of hydrogen would react with one volume of chlorine. And you form as a product in this case 2 volumes of hydrogen chloride. All right, and in order for that to work, the only way that can work is if hydrogen and chlorine combine in a 1 to 1 ratio to make two molecules that each have one hydrogen and one chlorine. All right, because if hydrogen and chlorine combine in a different ratio, you wouldn't be able to make two molecules of them, so the volume that you form would not be 2 in that case. All right, so that's again a little bit of a thought experiment, just to give you an idea of how that worked. Again, we're not going to go into a lot of details with that, but that's just some of the early experiments that were done to then not only just talk about the atoms that make up elements and compounds, but more specific information about the ratio that they combine and how we can determine their chemical formulas. All right, so any questions on stuff we've covered so far today? All right, so we're going to transition now into the second part of this first chapter, which deals with the actual structure of the atom. So it had been established that elements are made out of atoms. They're these little tiny indivisible units of matter that can't be broken down further, but are they just solid masses like the world's tiniest marbles, or do they have, additional little, substructures in them, additional components that make up the atoms, and how exactly are atoms of one element different from another? And so those are some of the unanswered questions that were then addressed next, using, again, the scientific method to study things. And so people, having established that atoms make up all elements, started doing experiments to try to figure out more about those atoms. And so one of the key experiments that was done is called the cathode ray tube experiment, which was done by J.J. Thomson. Now, I'll point this out from time to time. You'll notice that all these photos of old scientists that I have, they just look extremely unhappy. I mean, they made some of the most important discoveries in human history, and they're just not thrilled about it at all. I don't know why that is. But anyway, so that's J.J. Thomson, and we're not going to ask you to name, match faces with names or anything like that, but just to show you what he looks like. And so his experiment involved the following. So he took different elements and he applied a high voltage to them. And when that happened, a beam of particles came off of those elements, which he called the cathode ray. And he studied that cathode ray and its properties. Okay, so this cathode ray that he produced, it's called cathode ray because it occurs at the cathode of his electrical setup, cathode being one of the electrodes, not an important detail. But these cathode rays are repelled by the negative pole of an electric field, which tells him, you guys should know by now that like charges repel each other, so that means that these cathode rays are negatively charged because they are repelled by the negative pole of an electric field. Okay, so everything, he was producing these negatively charged particles. And he called them electrons. And what he found also was that these electrons are produced by many different substances in this cathode ray experiment. So it's not just exclusive to one element or another. Pretty much every element he tested that worked in this experiment produce these same electrons, or even compounds that he tested. And the properties of those cathode rays that were produced by every material are the same. So he studied also, how much does that cathode ray bend in an electric field, which is related to how much charge is in there. And that was the same, identical for every substance that he studied. So what he concluded then was that every substance, every element, every compound includes these negatively charged electrons that are identical from one compound to another, or one element to another. So every element has identical electrons as part of its atomic structure. Okay, so he concluded that all atoms contain electrons. And he also determined the mass to charge ratio of the electrons. So this experiment alone cannot cannot determine these absolute numbers, but you can determine the charge to mass ratio of the electron, which again was identical for all electrons produced by all substances. So it's identical particles, identical electrons found in every form of matter that he studied. Okay, so that was sort of the discovery of the electron, if you want to simplify it that way. So he discovered the electron, which is the negatively charged particles that are parts of atoms. And then from there was another key experiment that was done to learn even more about the electrons. And this is called the oil drop experiment by Robert Millikan, who is equally displeased with his discovery, or maybe even more so. All right, so Robert Millikan did this oil drop experiment. All right, so basically what he did was, you know how you can use it's not so common in Houston because you have so much humidity here, but where I grew up in Ohio, if you take a balloon and rub it on your head, you get really massive static electricity. So he wasn't using a balloon in his hair, but he was using oil droplets, and then he was putting an electric charge into them to basically make these oil droplets negatively charged, kind of like you would with static electricity. So he made these negatively charged oil droplets that were falling through this chamber, and then at the bottom of the chamber he had an electric field that was opposing those, and he turned up the electric field until the oil drops were stopped in air. And so basically when the force of the electric field matches the mass of the oil drops, that means the forces are balanced. Think about your free body diagrams if you've taken physics. And by doing that, by knowing how strong an electric field it takes to completely stop the motion of those oil drops, you can figure out the exact charge on each oil drop. So that's what he did. He measured the charge of each of these oil drops that way. All right, so let's look at the key observations. So again, falling and negatively charged oil drops can be stopped by an electric field. And what he found is, again, he can measure the charges on these different oil drops. And some of them, they had different charges from each other. Not all the oil drops had the exact same charge. But when we looked at the relative charges of the oil drops, they always occurred in regular intervals. So if one oil drop had a charge of 1 unit, the other oil drops would have charges of 2, 3, or 4 units, but not 1.7 or not 2.3 or something like that. So again, always regular intervals of the charge, not, again, continuous ratios. All right, so the charges on these oil drops always occur in regular whole number intervals in a relative sense. So we'll talk a little bit later how the charge on one electron is negative 1.6 times 10 to the minus 19 coulombs, which is the SI unit for charge. So that means if you measure that as the charge of one oil drop, another oil drop could have a charge of twice that, 3.2 times 10 to the minus 19th, or 3 times that, 4.8 times 10 to the minus 19, but it cannot have some interval in between those numbers. So basically what that tells you is that electrons are discrete particles, and each electron has an identical charge as any other electron. And he was then able to determine the exact mass and charge of the electron using this experiment. All right, so the previous experiment gave us the ratio of the two, but now with this experiment, in addition to that, you can determine the mass and charge separately. So this is how the charge of an electron was determined, and again, it sort of proved that electrons are discrete particles, and every electron has identical charge as every other electron. So they're, again, an identical particle that's found in all forms of matter. So those were the two key experiments to discover electrons and characterize them a little bit. So then the question became, well, how are the electrons arranged in the atom? So if you have negatively charged things in an atom, you must also have positively charged things, because atoms are not charged overall, they're charged neutral. So whatever negative charge you have in there from the electrons must be balanced by positive charges from something else. And again, at the time of the discovery of the electron, that was still a bit of a mystery. So the first model that was proposed, a model is kind of like another name for a hypothesis or a theory. The first model was called the plum pudding model. And again, this was proposed by the same scientist who discovered the electron, Thomson. All right, so again, we now know that there are electrons in atoms. That has to be true. There has to be positive charge. So the first proposal was that the positive charge in an atom was just a diffuse blob of positive charge, and the electrons were kind of floating around in there. And it was called the plum pudding model because in plum pudding, which is shown here, you have this sort of cake-looking substance and then little raisins or plums that are dispersed in there. So the plums or raisins would be the electrons, and the cake that's holding them together would be the protons, or the not called protons at the time, but the positive charge. So that was the first model, the plum pudding model. Now, if you ask me, the picture of plum pudding that I have at the bottom looks more like a cake, but I understand that this is popular in the UK, and I won't. I guess I'll defer to our British overlords on the proper use of English language. So it's called plum pudding, and this was the model that was analogous to that, which says that the atoms consist of electrons that are held in place by a diffuse cloud of positive charge. And so basically the electrons are randomly embedded in this cloud of positive charge. All right, so there's no regular arrangement of the electrons. They're not moving in regular orbits or anything like that. It was just, you got these little particles called electrons, and they're just floating around in this blob of positive charge. That's what the plum pudding model was. So that was the first proposal for what an atom might look like. And it turns out it was wrong, as very often the first proposals are wrong in science. So when you come up with a model or a theory, what you always do, of course, is you test that model by doing an experiment. That's the scientific method. And so one of the people that tested that model was Rutherford, who did the gold foil experiment. So Ernest Rutherford, I don't have his photograph here, but he did what's called a gold foil experiment. All right, so in every experiment you do, you have a hypothesis or an expected outcome. So let's talk about that first. So the experiment involves taking what are called alpha particles. These are positively charged and very heavy particles, and he just blasted them at a thin sheet of gold foil. Now, if the plum pudding model is correct, what should have happened, the hypothesis that would follow from that model, is that those positively charged alpha particles should just bust right through. Imagine taking a piece of paper and shooting a BB gun at it. It's kind of like that, just blasting right through it. That's what they thought would happen if you had this, diffuse cloud of positive charge making up atoms. The alpha particles, which are heavy and dense, would just plow right through it. So that's what they thought would happen. So these alpha particles, I'll use the Greek letter alpha to abbreviate alpha, they would mostly just pass through unimpeded. Or maybe they would be slightly deflected. You might see a little bit of deflection of those particles, but basically they're gonna plow right through that gold foil. That's what they thought would happen. Now what happened instead is, it is true that most of them went straight through. So that part was correct, but the other things they observed were a little bit weird. All right, so that's what this experiment shows. Here's your alpha particles shown as these red lines here. This is your gold foil. Most of them go straight through, but they found that some of them were deflected and often at very severe angles, even coming like straight back at the source. So they were deflected in different ways and very severely deflected in some cases. Okay, so some were deflected at large angles or reflected completely back to the source. So deflected at large angles, meaning they were bent quite a bit in their path, or they were reflected completely back to the source. All right, so the explanation for this first is that the plum pudding model is wrong, but what they came up with as an alternative explanation is that the positive charge in the atom and most of the mass must be located in a very small region of space, which they call the nucleus. So the positive charge and most of the mass are in a very small area, which was called the nucleus. So this gold foil experiment, again, to put things as simply as possible, led to the discovery of the nucleus and a new picture for what atoms would look like. So instead of having a diffuse cloud of positive charge where the electrons are floating around, you have all of the positive charge located in a really tiny area called the nucleus. And then it's the electrons that are sort of flying around that nucleus in a diffuse cloud. And then another key outcome of the experiment, why did so many of the particles pass straight through? The reason is that atoms are mostly empty space. That's another conclusion of this. All right, electrons are tiny and they occupy a large area compared to their size, and so at any given time, most of the volume of an atom is empty. You have a tiny little nucleus at the center, electrons flying around in this diffuse cloud outside of that, but most of the atom is empty space, and that's why a lot of those particles could just pass right through. They went right through that empty space, they missed the nucleus altogether. Okay, but some of the particles that collided with the nucleus, those are the ones that came straight back at you because the nucleus is positively charged and very dense, and so that allows those particles to be reflected. So that's how the nucleus was discovered, and that led to this sort of new picture of the atom. Now what we're going to go into in chapter 2 is more details about how the electrons are arranged around that nucleus. So that's coming later, but for now we should appreciate that the most up-to-date picture of the atom involves a very dense nucleus with the electrons diffusely organized around that in some way. Okay, so that led to sort of a clearer picture of the structure of the atom. So let's summarize then what are called the subatomic particles, the three things that make up the atomic structure. So we talked about electrons first. I'll go in reverse order here. Those are the first ones that were discovered. They have a relative -1 charge, or in absolute sense in coulombs is -1.60 times 10 to the minus 19. So that was their charge. That was discovered again by those cathode ray and oil drop experiments. So those are the electrons. We'll talk about the mass here in a little bit. And then the other one that they know now must be present, you must have some sort of positively charged particle to balance that negative charge. And that positively charged particle was eventually called a proton, which is exactly equal in charge but opposite in sign to the electron. So electrons and protons have the same magnitude of their charge, just opposite in sign. So this one would be plus 1.60 times 10 to the minus 19. And then there's a third subatomic particle that wasn't recognized until more recently. So the origin story for the neutron is more complicated. It involves some pretty high-level physics experiments that we're not going to explain in this class. So for a while, they didn't even know that there were these things called neutrons, but eventually they figured that out too. And so also in the nucleus, both of these are in the nucleus. So I'll put a little label there. These are the two particles in the nucleus, protons and neutrons. Neutrons have zero charge, but they are also present in the nucleus. So there's these other particles in the nucleus that are called neutrons that are zero charge. Now in terms of the relative masses of the three, in what's called an AMU, an atomic mass unit, as we'll define more clearly later on, protons are about 1 atomic mass unit in a relative sense. Neutrons are essentially identical. So protons and neutrons have almost identical mass. For our purposes, they are identical. And obviously the only difference being the charge. Electrons, though, are tiny compared to these two. So the relative mass of an electron is 180 times smaller, or maybe it's 1800, sorry, 1800 if I'm not even doing my math right in my head. So 0.000549 is the relative mass of an electron in AMUs. So well over 99%, 99.9% or so of the atom's mass is made up of the protons and neutrons. The electrons are a very, very small part of the mass. So that's the relative masses, and then we don't really want you to memorize these numbers, but just to give you a sense for how tiny they are. So, you know, a penny, for example, is a few grams. That's kind of a scale we're familiar with, is like 1 gram or so would be about the size of a penny, or maybe a little bit bigger than that for a penny. But anyway, the absolute mass of a proton is 1.67 times 10 to the minus 24 grams. So it's extremely tiny. You need a lot of protons to make up even 1 gram, okay? So these are tiny numbers. That's just the point of showing them now, is to give you a sense for how tiny atoms are. Pretty much, again, the same mass for neutrons within, you know, 3 significant figures, 2 decimal places. Protons and neutrons are the same. And then electrons are, again, even tinier than that. So they're 9.11 times 10 to the minus 28 grams, which again is around 1,800 times smaller. All right, but these are the key subatomic particles, and especially the relative charge and the relative mass you should be familiar with for this course. And this reminds me of the time that a neutron went to a bar, and he asked the bartender, how much for a draft beer? And the bartender responded, for you, no charge. Okay, so that's the first joke of the semester. All right, so we're going to move on now to, we've talked about subatomic particles. Every atom is made up of protons, neutrons, and electrons. So then what distinguishes one atom from another? If you have an atom of one element, how is it different from an atom of another element? And that's what we're going to now talk about, and how we can sort of talk about that and sort of quantify it and systematize it in some way. So the key thing that distinguishes one element from another is the number of protons in the nucleus for the atoms that make up that element. All right, so that's what makes one element different from another, is the number of protons in the nucleus. So we'll give an example a little bit later on of carbon, a very common element on Earth. Each atom of carbon has 6 protons in the nucleus, and every atom of carbon will have 6 protons. If it has more than 6 or less than 6 protons, that makes it a different element. So every element has a distinct number of protons in its nucleus. And then we can use an atomic symbol then to indicate for each element how many protons, neutrons, and indirectly how many electrons are present. So the way that an atomic symbol works is, and I'll give you the definitions of these in a second. So you have a letter symbol, which I'll abbreviate here as X. It's either a 1 or 2 letter abbreviation for that element. That's what you would see on the periodic table that we'll talk in more detail about later. And then you have 2 numbers that can be associated with this symbol. So the first one is going to be abbreviated as A, and the second one's going to be abbreviated as Z. I'll do them in different colors just to keep things straight. Okay, so the first one, X, the center part of the symbol, is going to be called the atomic symbol. And it's going to be a 1 or 2 letter abbreviation for the element. And the first letter is always capitalized. That's what you'll see on the periodic table. As a note, something you may want to start brushing up on, it doesn't come up all the time on exams and stuff, but we expect you to know, to be able to match the symbols and the names of the first 36 elements. So the periodic table that you guys have, if you looked at it yet, only has the symbols on it. So you have to know the name of the element in some cases. Usually we don't bother with that too much, but you should know that C is carbon and Na is sodium for the first 36 elements, not for all 118 of them, but just the first 36, okay? So be aware of that. Just kind of make sure as you go through problems that you're able to match names and symbols when it's necessary. But that's not going to be a huge deal. All right, and then the other 2 parts of this are the 2 letters, or 2 numbers, in this case, Z and A. So Z is what we call the atomic number. So that's going to be in the bottom left of our symbol. And quite simply, this is giving you the number of protons in the nucleus. So we use P plus as an abbreviation for protons. And so Z is the number of protons in the nucleus. Now, you don't always see Z given in the atomic symbol because, again, each element has a distinct number of protons. So putting the element symbol X and the atomic number Z together is a little bit redundant, because if the atomic symbol is C for carbon, that means it must have 6 protons. You don't have to explicitly put a 6 there to indicate that. But, so you might see it, you might not. So Z is not always there, but that's what it means if it is there. It's the number of protons in the nucleus. And you should be able to figure out what Z is once you know what the element is. And then the second part of the name, which is A, which goes as a superscript, is called the mass number. All right, and this is going to be a new one that we haven't seen yet. But it's also relatively simple. It's going to be the number of protons plus the number of neutrons. Where I'll use N0 to abbreviate neutron. Okay, so that's whatever's in the nucleus for that element. How many protons and plus how many neutrons are in the nucleus of that element. Okay, so that's what an atomic symbol looks like. Now another important concept then to define, now that we know what an atomic symbol is what's called an isotope. Okay, so as we said, an element is distinguished by how many protons are in the nucleus, but it turns out that for a given element, sometimes the atoms don't have the same number of neutrons. Some of the atoms might have different numbers of neutrons. And so those are called isotopes if they have different numbers of neutrons. But again, same number of protons belonging to that element. So atoms of a given element that differ in the number of neutrons are called isotopes. And because they have different numbers of neutrons, that means their mass numbers are also different. So mass number is not a unique identifier for an element, because for some elements you can have different isotopes that have different mass numbers. They will all have the same number of protons for that element, but they might have different numbers of neutrons. Now sometimes that happens, so for some elements that exist naturally, 100% of that element is made up of a single isotope. But for other elements, you have multiple isotopes that are always present. So the example that I've been given a lot, which is carbon, has, it's like 99%, or at least 99% of one isotope. So most of it is one isotope that has 6 protons and 6 neutrons. But then there's also an isotope that has 6 protons and 7 neutrons, which would be carbon-13 is called, because the mass number is 13. That's like roughly 1%. And then there's a very small fraction of carbon-14, which you might recognize as being what's used in radioactive dating. That's also present, but not stable, so it decays over time. So there's 3 isotopes of carbon, for example, mostly one isotope, but a few minor ones. So that can be true where they have different numbers of neutrons. Now, when you have isotopes, the properties of isotopes for a given element are nearly identical. So it wasn't easy for people to tell that this was the case early on, because really the only difference between isotopes that's easily observable is their mass. So what they started doing was they started doing some experiments where they were able to measure the masses or the relative masses of individual atoms in a sample, and they found that for some elements they would produce multiple masses, and that's how they knew that something was going on with isotopes. But really it was the mass that was the only huge difference. If you have different isotopes of the element, usually the other properties, their chemical reactivity, their physical properties are almost the same as each other. It's just the mass that's a little bit different. So the properties of isotopes for a given element are nearly identical. All right, so here's some examples of isotopes. Let's go to the smallest atom in the world, which is hydrogen. So hydrogen has 1 proton in the nucleus. That's the smallest you can get. So the atomic symbol for hydrogen is going to be H. And if you put a 1 down here, that means that there's 1 proton in the nucleus, which again, that number doesn't have to be there. So one of the isotopes of hydrogen just has 1 proton in the nucleus and 0 neutrons. So if it has 1 proton and 0 neutrons, that means the mass number is 1. 1 plus 0 is 1. And so that would be one isotope of hydrogen. That's the most common isotope of hydrogen. So this one would have 1 proton and 0 neutrons. So that's one isotope of hydrogen. Now there's another one. For most elements, the isotopes all have the same names. For hydrogen, we give them unique names. So the second isotope of hydrogen, which has 1 proton and 1 neutron, so it adds 1 neutron to the nucleus, still has an atomic number of 1, but now has a mass number of 2, because the sum of those two is 2. So that is often called deuterium. So if you've heard that word before, that's what deuterium is. It turns out that the isotopes of hydrogen are maybe the one case where the chemical properties are significantly different because the mass is doubled between the two isotopes. So for most elements, if you add one neutron, you're not going to change the mass a lot compared to the mass of the whole atom. But here we're doubling it. We're going from a mass number of 1 to a mass number of 2. And that changes the properties a lot. It turns out if you drink water that has 100% deuterium in it, so D2O instead of H2O, it really messes up your metabolism to the point that if you drink too much of it, you can die. So don't do it. It's also probably the perfect crime because it's hard to, if you poison someone with D2O, it's hard to tell because it looks the same as water, and they're not going to be easily able. I didn't tell you guys that, so you didn't hear that here. All right, so that's deuterium though. So that's the second isotope of hydrogen, and then the other one that is radioactive and not very common. I think this one's only man-made, but it does exist. Has 1 proton and 2 neutrons, and so that would be called H3, or it has another name, tritium, as well. So that's used in a lot of biological studies for radioactive labeling. Okay, so those are the 3 isotopes of hydrogen. All of them have 1 proton, different numbers of neutrons that distinguishes them as isotopes. So that's what I mean by isotopes. And this was the one part, as I mentioned earlier, where Dalton's atomic theory was a little bit wrong, because Dalton postulated that all of the atoms for a given element have identical masses to each other, and that's not necessarily the case if you have isotopes. So you can have a mixture of isotopes. Most elements occur as a mixture of isotopes where some of the atoms are going to have different masses than others, again, determined by how many neutrons are in the nucleus of that isotope. Okay, so that's the concept of isotopes. Let's just do a couple of sample problems with isotopes to learn how to use atomic symbols and how to calculate some of these simple things. So we have this element here, palladium, which is it's a precious element that's used in some jewelry. It's also used in catalytic converters in cars, so it's pretty expensive stuff. And it has 2 major isotopes that have mass numbers of 106 and 108. Okay, so we want to determine the number of protons, electrons, and neutrons in both of these isotopes. So when you're doing problems like this, you'll see these in the homework assignments and tests where you have to calculate number of subatomic particles. Again, the easiest one to look for is the atomic number, because that directly gives you the number of protons. And that's going to be distinct for that element. So the number of protons in this isotope is 46. That's directly given by the atomic number. To get the number of neutrons, we have to do a little bit of math, because again, this mass number here is protons plus neutrons. So what we need to do is we need to take the mass number, which we abbreviate as A, and then subtract the number of protons to leave how many neutrons there are. So that's going to be 60 in this case. So 46 protons, 60 neutrons gives us a mass number of 106 when you add them together. So again, it's just a little bit of algebra to solve for how many neutrons there are. And then finally, for the number of electrons, we haven't explicitly talked about this yet, but elements are uncharged, when they exist naturally, they're uncharged. So if you have no net charge, if you know how many protons there has to be equal number of electrons, because the electrons and protons have the same charge but opposite. So however many protons you have to have the same number of electrons to balance the charge if it's a neutral element with no net charge. So in this case, the number of protons and number of electrons has to be equal because there's no charge, which means that number is also 46 because it's a neutral atom. We'll talk about ions either later today or next time, which are atoms that have a net positive or net negative charge. In that case, the number of protons and electrons are not equal. But if it's a neutral atom with no charge, then they have to be the same, number of protons and number of electrons. For the other isotope, most of the numbers are the same. So for this second isotope that has a mass number of 108, it's the same element, palladium. So this atomic number here is the same, and that means also the number of electrons has to be the same. So the number of protons and the number of electrons are both still the same, and they're both still 46. All right, it's still palladium, so that has to be true. But then if we calculate the number of neutrons for this isotope, the mass number is now 108. We still have 46 protons, so when we subtract the number of protons, that leaves how many neutrons there are, which is now 62. So again, the only difference between isotopes is how many neutrons are in the nucleus. Number of protons is the same, number of electrons is the same, provided they're uncharged, and now all we have is different numbers of neutrons. They just differ by 2 in this case. So those should be pretty straightforward, but just make sure you know what each of those numbers means and how they relate then to the number of subatomic particles. And then the second sample problem that I'll do on this topic is if we have a fictitious element, a made-up element with symbol Q. There is no element with symbol Q. I guess in light of recent political developments, I shouldn't use the symbol Q anymore. But anyway, this was made a long time ago before QAnon existed. So a fictitious element with symbol Q has 34 protons and 43 neutrons. Write a proper atomic symbol for this element. Okay, so again, the proper atomic symbol would have the atomic abbreviation in the middle, the atomic number Z at the bottom, and the mass number A at the top. So again, Z is the simple one because that's just the number of protons, which is given here directly as 34. A is the mass number, which is protons plus neutrons. So that's 34 protons given to us in the problem, 43 neutrons also directly given to us, which comes out to 77. So if we want to write an appropriate symbol for this element Q, the letter symbol goes in the middle, the atomic number goes at the bottom, which is 34, the mass number goes at top, which is 77. And so that's sort of going the opposite direction, taking the number of subatomic particles that we give you and generating the atomic symbol. Now in Blackboard, we can't easily ask you to type in atomic symbols, but it could be a multiple choice question of this type where you have to select the correct symbol based on the information that we give you. Okay, so any questions on atomic symbols or isotopes? Okay, we're going to try to plug forward since my tablet is behaving and we got a little bit behind last time. So let's go and talk a little bit about the formation of ions as sort of the last thing we'll cover today. Or one of the last things anyway. Okay, so if you have a neutral atom, as we talked about, they contain equal numbers of protons and electrons. An electron will use E minus to abbreviate. Protons, electrons, and that has to be true to balance the charge. So if the overall charge is 0, you need to have equal numbers of protons and neutrons. Or sorry, electrons, protons and electrons. Now when you form ions, the only way that you can form an ion, which would have an unequal number of protons and electrons, is to add or remove electrons. Remember, we never mess with the number of protons in the nucleus because that would change the identity of the element. If we're forming an ion for that element, we're either going to add electrons to make it negatively charged, or we're going to subtract electrons to make it positively charged. All right, so to reiterate that point, we're never going to remove or add protons to the nucleus. Because if you do this, this would change the identity of the element of the atom. So that's not going to form an ion, that's going to form a whole new element.
What's that say? The remove blank?
Never remove, oh man, I'm all over the place here. Remove or add, I should say. So you never change the number of protons in the nucleus, because by doing that you would form a whole new element. So when we're forming ions, we're only going to be dealing with electrons being added or subtracted. So it changes the identity of the atom if you do that. All right, and so what you want to do then is if we know the charge of the ion, that means you need to add 1 electron for each negative charge if that ion is negatively charged. And you're going to subtract 1 electron for each positive charge if it's a positively charged ion. All right, so you're going to have an imbalance then in the number of protons and electrons where the difference between those determines what the charge is and whether it's positive or negative. If you have more protons, it's going to be positively charged. If you have more electrons than protons, it's going to be negatively charged. All right, so again, this is perhaps best approached with some examples. So now we can give you atomic symbols that also have a number here in the top right that indicates the charge. So this would be a symbol for an ion, not a neutral atom anymore. So IR is iridium. If you remember one thing in this course, iridium is my favorite element. Everybody should have a favorite element, and maybe you'll discover yours in this course. But anyway, iridium is mine, and so if you have an iridium 3+ ion, meaning it's an iridium atom with a net charge of +3, let's figure out how many protons, neutrons, and electrons are in there. So the number of protons, again, is given by the atomic number and is distinct for that element, which is going to be 77. So there's nothing different there. The number of neutrons is given the same way also as before. The mass number is not affected by the charge, so we just take that mass number, which is 192, We subtract how many protons there are to figure out how many neutrons would be part of that nucleus as well, which is 115. So as you get to heavier and heavier elements, you tend to have more neutrons than protons. That's a general trend. But then to find the number of electrons here, if this was a neutral element, the number of electrons would be the same as the number of protons, which is 77. But the charge is +3, which must mean we have 3 fewer electrons than protons. You have to have an excess of protons in the nucleus to have an overall positive charge. So for a negative charge, that means there's 3 less electrons than protons, which would be 74. So the only difference between this ion and the neutral atom is that instead of 77 electrons, we now have 74, which means that the net charge is +3. Now, if we have a negatively charged ion, it just goes the opposite way. So protons is still given by the atomic number, which is 16. Neutrons comes from the mass number 33 minus the number of protons, which means we have 17 neutrons. So those, again, same exact determination, so I'm not going to go through them in a lot of detail. But then for the number of electrons in this case, there are 16 protons in the nucleus, but the overall charge is now -2, often written as 2 minus, but that just means -2, -2. So if you have a -2 charge, it means you have 2 extra electrons. So we need to add 2 electrons to make the charge unbalanced in favor of the electrons, which makes it 18. And again, that comes from the -2 charge. Actually, that's this part of it. So we add 2 electrons if the charge is negative. All right, so when we're dealing with symbols for ions, the only difference is you're going to indicate a charge in the top right, and that's going to lead to different numbers of protons and neutrons. The last thing that I'll cover then, I'll leave the last example for you to do on your own. I'll write it out before I post the notes. The last thing I'll cover is how we use the periodic table to find the number of protons. So as I said, the atomic symbol often leaves out the atomic number because that's distinct for whatever that element is. And when you look at the periodic table, which we're going to cover in a lot more detail later, you'll see that each element has a little box like this. Ours does not have the name of the element, as I said, so that you'll have to know for the first 36 in some cases. But what we have here is in this block, we have the symbol, which is the letter that abbreviates the element. This number up here is the atomic number. So if you look at the periodic table, they're arranged in order of atomic number, and then the atomic number for each element is clearly indicated in that box for the element. All right, which again is the number of protons. So from the periodic table, we can easily figure out the number of protons. We don't yet know what this number means here. It's related to the mass number, but we haven't covered it yet, so don't worry about it at this point, why it's 12.01 and not a whole number. But this is related to mass number, but we'll cover it later, so I'm just going to move on from that from now. But now if you're doing problems on the homework assignment or the test, you will always have access to the periodic table. We never take that away from you. So if we're asking about the number of protons and we don't specifically indicate it in the symbol, you can just look it up on the periodic table to figure out what that should be. So as a note here, which I've already sort of mentioned, but now I'll state it more explicitly because it's important at this point. This atomic number Z, which I gave in the symbol in the previous example, is usually left out of the atomic symbol. So, for example, if we have the most abundant isotope of carbon, which is a mass number of 12, this would be the full symbol. Mass number has to be indicated to tell you what isotope it is, with the atomic number in the bottom left, but that is often going to be just written as 12C without the 6 there, okay? So this is the more common way you'll see it. So when you're doing homework problems, you will often not see the atomic number given directly in the symbol, just have the isotope mass number and the symbol itself. So this is the more common way of looking at it. And the reason is because the atomic number Z is redundant with the symbol. If it's carbon, if it's C as the abbreviation there, it has to have an atomic number of Z. It never will have anything else because carbon is always an atomic number of 6. Remember, the atomic number designates what element it is. So if we don't give you the atomic number in the symbol, you just look up that symbol on the periodic table, and the number right above that tells you what the atomic number is. That's how you'll get it if it's not directly provided to you in the atomic symbol. All right, so we got through everything that I wanted to. There's just one more example problem, which I'll fill out and put it in the notes, but you'll have to do it on your own to see if you can get it right, so it's a good practice. If there's any last questions, let me know now, and if not, I'll close this up and see you guys next week. All right.
My notes on Dalton. Do you recommend using like the printed out, like your notes or notes?